Hello, Professor.
Hey, how's it going?
Good, sir. How are you?
Good, good.
How's your day going?
It's good. Had a lot of meetings today, but
Oh, really?
I'm done for today though. So now it's just classes from here now.
Oh, I see.
How's your day?
I'm busy. Yeah, I had to go get my car fixed in the morning.
Oh,
I
dang.
came back straight to classes until 5,
Oh,
and
wow.
then I got to work from 6 up to midnight.
Oh, wow. Dang. It's a busy day.
Yes, sir.
Where do you
Very.
work?
I work in school actually.
Hmm.
Yes, sir.
At you mean on campus?
Yes, sir.
Oh, cool. What do you
I work
do?
in the police department.
Oh, nice. That's awesome.
Yes, sir. I mean, it pays the bills, so.
That's good. That's good.
Oh, Professor, I just wanted to ask you in regards to like midterm one.
Sure. Mm-hmm.
Like I didn't have enough time to finish like the last question, and apparently it was like 15 minutes, 15 points,
Yeah, yeah. Uh-huh.
and I like my grade wasn't like the best. Like I think I got like a 26.
Mm-hmm.
I was just wondering like if it's like still possible to get like a really good grade.
Yeah, no, it's definitely possible. So, that was kind of the first. You guys were kind of the first trial that I've tried like a timed midterm exam virtually like that. And I know everyone's experience is a little bit different, but typically what I do is that because usually because midterms always come at a time when things are usually busy. I usually give students the opportunity that like if they if they don't do that well on the midterms but you do really well in the final, then I'll use the final and I'll replace one of your midterm scores, with whatever your final exam score is. And so, in the final, if you kind of calculate it, the midterms, each of the midterms are 20%, and there's two of those, and the final exam is 40%, and there's one of those. And so, if you do, even if you do really poorly on both the midterms, if you do really well in the final, that's going to overwrite all your midterm scores. And so, basically right up until the end, you have 80% of the points available to you. And the other 20% are the homework grades. So as long as you're keeping up with the homeworks and you do well in the final, then you can turn it around basically at any time in the class.
Understood. Thank you.
Mm-hmm. Yeah, I can do that. I did post the exam solutions, and so you know, you can look at those. And actually, there were two versions of problem 6 on the exam as well. I think for problem 6, I think I just changed the numbers around a little bit, but you can look at the midterm solutions online. But I'll go over it quickly in the class today. Mhm.
so sad. Justin.
Okay, it's 2:30, so let's go ahead and get started with the lecture today. All right, good afternoon, everyone. How's everyone doing today?
Pretty good.
Good.
Tired of midterms.
I know it's right in the middle for you guys, so I'm sure you guys must be pretty tired. Speaking of our midterms, I did finish grading those on Monday night, and so you should see your grade on Canvas as well. Are you guys able to view my feedback? So in addition to your grade, you should be able to look at the midterm again. And you should. I left comments on every single one of your problems. So are you guys able to view that?
Yeah, I was able to see them.
Great. Okay, great. So you guys did pretty well overall on the midterm, and so the average was basically 75% right on the dot. So I think out of 50, I think the average was about 37.5 out of 50. I think that's kind of what I saw on my kind of grading sheet kind of as I was doing it. So you guys did well. So I mean it was a good midterm. Okay? And so if you did well in this midterm, great. But if you didn't do, if you didn't perform as well as you would like, I was telling someone before the class today that this is not the end. And so usually what I offer, and this is for all my classes, that if the midterms don't really go the way that you want, and that can happen for various reasons, because things get really busy throughout the semester. I give you guys a chance to make it up on the final exam. And so if you get a better score on your final exam than you do for your midterms, then what I'll do is I'll replace your midterm scores with your final exam. So if you didn't do so well here, you still have a chance to make it up later on in the semester. Okay? Another thing that I usually do with my classes, which I haven't done in a while, just because kind of over time, the averages have kind of been going up for my classes, is that I like to scale my final course grades. And so what that means is that, after all the grades are put in for all the final exams and everything, if the overall class average is below a 75%, what I like to do is I'll add a flat amount of points to everyone's grade, and just to make it so that the average is 75. And so, if things keep going the way that they are, and the averages are like this, then I'm probably not going to do it. But if the midterm 2 and the final exam, those are kind of below 75%, then you can expect a little bit of a boost, basically once we get to that stage. But as of right now, with these midterm scores, I don't anticipate doing any of that. Okay. All right, and so there was a request before the lecture today to go over problem 6 on the homework, which I think was the air fryers question, and so that was the Num Capacitance problem, and so I will go over that briefly. But if you want to look at my solutions for the midterm exam, those are also up on Canvas as well, and so you can find those. I think the easiest way to find those would be go to the file section on the Canvas site, and then click on the folder for solutions, and then you'll see a new PDF has been uploaded for the midterm 1 solutions. And so if you want to look at my solutions, it's there for you. Just note that for every problem on the exam, there are basically 2 different versions, and which version of a problem that you got was kind of randomly chosen by Canvas. So you'll see kind of 2 versions of every single question. So just try to find the one that kind of matched up to to the one that you got, so that you can kind of see my responses for that. Okay, and that goes for both the short answer questions and also both the problem solving questions. Okay. Okay, and so right after this, I'll just go over very briefly the Num Capacitance problem, which was the air fryers one, and then we'll pick up where we left off on Monday about convection heat transfer. Okay. So besides that, are there any questions that I can answer? Okay. All right. So let's go over question 6 on the exam. Right, and so this problem was about air fryers, basically. Right, so the one thing I don't like about the Canvas, quizzes is that you can't see the titles of the problems that I gave you. Right? But basically, I wanted you to analyze an air fryer. And so if you do any cooking in your kitchen, you've probably heard of an air fryer at this point. Okay? And basically, how it works, or how it's advertised to work, is that it allows you to get crispy food as if you deep fried something without all the trouble of all the oil, right? But in reality, you know, the air fryer itself isn't anything new. So, you know, the invention of an air fryer, you know, it's actually more of a marketing thing more than anything. Because, you know, way before air fryers existed, there was a kitchen appliance called a convection oven. And so the way a convection oven works is that it basically blows hot air over your food to make it cook faster than a conventional oven. Right? And so all the air fryer company basically did was they kind of just rebranded that. And so, you know, it's not anything new, but you know, it's really popular nowadays. But you know, you've been able to buy convection ovens for, you know, for a long time now. Okay, and so in this problem, what I wanted you to do was analyze one. And so basically the situation is this. And so you have, you know, your parcel of food inside your air fryer, okay? And then the way it's going to cook is that we're going to blow hot air over. Okay? And so I'm going to do the A version of this problem. So in the A version, the air is at a temperature of 200 degrees C. The convection coefficient we assume is going to be 50 watts per meter squared K. The density is 1,060 kilograms per meter cube. Okay. The surface area is equal to 0.03 meters squared. The volume will say 0.0016 meters cubed. Okay. And C is 1.77 kilojoules per kilogram K. Okay. All right. And so in this problem, you know, basically what we're going to do is we're going to use the Num Capacitance method to solve for the temperature evolution of the food as a function of time. Okay. And so, you know, I think in the problem, I basically say that, you know, you can assume that the Num Capacitance method is valid. And so you can go ahead and do that. Okay. All right. And so the first thing that we note, because, you know, eventually we're going to use this with the general Num Capacitance, let's note, you know, all the different forms of heat transfer that we have here. Okay. And so first thing, you know, we should know is that, you know, because we have convection here, you know, we're going to put a check mark next to convection. Okay. And so we're going to have that active in our situation. Next, we're going to have, you know, next we're going to look at heat flux, right? And so I did see a lot of people, you know, include the heat flux in their equation because I think that was kind of similar to the homework. But in this problem, you know, there was no heat flux that was given to you. And so the heat flux term is not going to be there. And then lastly, we have the generation term. And, you know, there was nothing in this problem that said anything about generation. And so the Q dot is going to be 0. Okay. And so now let's kind of work through all the different parts of this problem. And so the first part asks you for the initial excess temperature of the food. And so the initial, remember, excess temperature is our theta value. And the way that we compute this is we take the temperature of our object and we subtract the temperature of the fluid. Right? And so I think in this part of the problem, it told you that the initial temperature of the object was 15 degrees C. Okay? And then all we need to do is just subtract the temperature of the fluid, which is this guy up here. Right? So basically we're doing T minus T infinity. And so this gives us minus 185. Okay. Right. And so that's all part A. So part A was just to basically help you solve for theta I. Okay. Okay. And then we got a minus 185. And then the next part of the problem is we're going to use the general Num Capacitance method to basically solve for theta as a function of T. Okay. Any questions on this so far? Okay. All right, and so now next let's do, you know, let's start with the general Num Capacitance, and then we'll cancel out some terms due to our assumptions. Okay. All right, and so general Num Capacitance looks like this, and so we have d theta dt plus HA over rho VC theta, right? is equal to Q dot over rho C plus QS double prime AQ over rho VC. Okay. All right. And so let's look at each of these terms and let's cancel some out, according to our situation. Okay. All right. And so first we have the unsteady term, and so we always include this guy, so that's fine. Okay. Next, this guy here is our convection term because it's the only term with H in it. Okay. And since we have a convection oven or an air fryer, we're going to keep this guy. Okay. Next, we have Q dot, which is our generation term. Okay. Since there's no generation here, we're going to go ahead and cancel that out. Okay. Finally, we have our heat flux term, which is our QS double prime. And we said earlier that there's no heat flux. We can go ahead and cancel that guy. Okay. And so in the end, what we're left with is d theta dt plus HA over rho VC. And so we have all of these variables from the from that's given to us in the problem. And so we go ahead and plug all of those in. Okay. And so if we plug in for H, we plug in for A, plug in for the density, plug in for the volume and C, what we get is 0.0005 theta. Okay. And all this is equal to 0. Okay. All right. And so what we have from here is we have a differential equation, but this differential equation is separable. Okay. And so this is kind of the main mistake that I saw a lot of people make with this, because I think from here what they did was what you guys did was you kind of just subtracted this term to the left-hand side, and then you treated it as a constant. But because we have this theta right here, we need to solve this with separation of variables. Okay. And so, once we do that, we subtract this term to this side and then divide both sides by theta. What we get is d theta over theta is equal to minus 0.0005 dt. Okay. And so if we integrate this guy, what we get is ln of theta is equal to minus 0.00005 t plus c. And then we exponentiate this and we get theta of t is equal to a e to the minus 0.0005 t. Okay. And so this is kind of like the very first kind of Num capacitance method that we did, right? And so once we eliminate generation and heat flux, this is kind of the exact situation with just convection. And when we plug in the initial condition here, what we see is that this A is going to be the same thing as theta I, or initial excess temperature. Okay? And so what we get in the end is theta of T is equal to minus 185 E to the minus 0.0005 T. Okay? And that's the solution for that. Okay. Any questions on this? Okay. All right, and so that's part B. And then part C asks you to basically take this solution right here and solve for the amount of time it takes for the food to reach 75 degrees C. Okay. All right, and so to do this, we have to basically compute the excess temperature at 75 degrees C. Okay. And so just like we did in part A, we're going to do 75 minus the air temperature, which is 200. And what we get is minus 125. Okay. And so this is going to be our theta, which we're going to plug in back into our answer for part B and then solve for little t. Well, I mean, I wrote the question, so I know the I know how to do these. So it's so yeah. I took my version of the test. I actually took the test twice because I had two versions of the test, and then so I did the test twice already. Okay, and so now let's go ahead and plug this in. And so we have minus 125 is equal to, on this side you can see we have minus 185 e to the minus 0.0005 t. Okay. And then from here, we can just use algebra and solve for little t, okay? And so let me divide both sides by 185. And so we have 125 divided by 185 is equal to e to the minus 0.0005 t, okay? Right? And so from here, we need to take the natural logarithm both sides in order to get this guy out of the exponential, okay? And then, we take the natural logarithm, we divide by, minus 0.0005, and what we get is t is equal to, because this ln is going to cancel with that, ln of 125 divided by 185 divided by minus 0.0005. And then you plug that into your calculator, and what you get is 784.1 seconds. All right, and so that's the version A of this problem. And so version B, you kind of just run through the same thing. It's just the numbers are slightly different. Okay? But for problem 5, the two versions of the problems are actually quite a bit different. And so definitely check out the solution for that one if you're if you're looking at that. Okay? All right. So any questions on this before we get back into convection? Okay. All right. And so definitely, check out your midterm scores, check out the feedback that I gave you. So I try to leave, as descriptive comments as I could, and then check out the midterm solutions for, the problems that you missed. Okay. All right. And so let's pick up, where we left off on Monday. I think we were kind of near the end of lecture notes 5, which was, our introduction to convection. Okay. And I believe the last thing that we were talking about was the non-dimensional numbers that we're going to use for convection. Okay. And so, we've already gone over, the first two. So the first one that you're going to need is the Reynolds number. The next is the Nusselt number. And I think we kind of left off on our discussion of the Prandtl number. So this PR right here stands for Prandtl number. Okay. And the Prandtl number is going to be the ratio of the kinematic viscosity over the thermal diffusivity. Okay. And what we were saying was that, this number right here kind of is a ratio, or it kind of compares, the fluid mechanics of a situation versus the heat transfer almost. Okay. Because remember what we were talking about was the viscosity is a measure of how well momentum, diffuses within a fluid. And then your thermal diffusivity is how well energy transfers in the fluid. Okay. And so this is basically a ratio of momentum diffusivity all over thermal diffusivity. All right. And so, those are kind of, long words without, much physical meaning. And so let's talk about, what these kind of physically mean, right? And so, last week when we were talking about convection, we spent a lot of time talking about boundary layers, right? And so, these parameters here, the viscosity and also the thermal diffusivity, these have a strong effect of, how quickly the boundary layers kind of grow relative to each other. remember we have two boundary layers. We have one of which is the fluid boundary layer or the momentum boundary layer, and the other boundary layer is the thermal one. Okay. Right. And so kind of the most balanced case for this is when Prandtl number is equal to 1. Okay. And just kind of for your own reference, Prandtl number equal to 1 is true for most gases. Okay. Right. So most gases will have this Prandtl number equal to 1. And so when Prandtl number is equal to 1, basically what we say is that both the fluid boundary layer and the thermal boundary layer grow at the same rate. Okay. And so, when you have fluid striking a surface, then you have both boundary layers and they're basically almost kind of right on top of each other. Okay. Okay. Any questions on this so far? Okay. All right. And so what happens when Prandtl number is much, much less than 1? Okay. And so for Prandtl number much, much less than 1, what this tells us is that, energy moves very easily in this fluid, but momentum does not. Okay. Okay. And so one example of a liquid with Prandtl number much less than 1 is liquid metal. Okay. We know that, all metals, because of their molecular structure, they conduct heat extremely well, right? And so if you have a liquid metal, your energy is going to go really, your energy is going to travel really quickly, but, the momentum is not going to travel all that much. And so your fluid boundary layer will be kind of really slow to grow, right? And so to just draw an example, let's say that we have liquid metal that's striking this surface right here, okay? And this surface might be at a higher temperature than the fluid. And so what's going to happen is that, for your thermal boundary layer, it's going to grow just really quickly like that. Okay. Meanwhile, your fluid boundary layer is going to grow much slower because the Prandtl number is much less than 1. Okay. Okay, and so because the fact that Prandtl number is much less than 1, we know the denominator there is going to be much, much higher. Okay, and that tells us that energy is going to travel a lot faster. Okay? All right, and so the last case that we can have here is if Prandtl number is much, much greater than 1. Okay? And so these are cases where energy doesn't travel all that easily in a fluid, but momentum does. Okay? And so, you can kind of think of it as kind of the opposite of the situation that we have up there. Right. And so one example of a liquid with Prandtl number much greater than 1 would be something like oil. And so oil is, relatively, decently viscous. I mean, it's not like honey, but if you stick your hand in a jar of vegetable oil, a lot of it's going to come up with you because it's fairly viscous, and it feels kind of gross in your hands. So don't do that. Right? But actually, oil actually doesn't conduct heat all that well. And so, if you have oil that's flowing, what you'll see is that the fluid boundary layer will develop a lot faster. Okay. And so, the reason I bring up all these non-dimensional numbers is that they're going to form basically the core of our convection analysis. Okay. Because basically what we're going to see is that, starting in the next section, ultimately what we want to solve for is the Nusselt number. Okay? Because we've already kind of established that computing H is really hard for, for a generic kind of fluid flow convection situation. But, what's slightly easier than this is to compute the Nusselt number. Okay? And if you remember from last class, we saw that the Nusselt number kind of had the same expression as our Biot number, which was H times L divided by K. Okay. And so if we can find the Nusselt number, we can then use that, and we basically just multiply it by K and divide by L, and then we'll be able to compute H for that situation. Okay. And so the Nusselt number is basically going to be our gateway. It's going to be our key to basically solving for H in kind of, these convection situations. And it turns out, there's been a ton of experiments done, over, the many years, way before I was alive. People have found out that, for general kind of, convection situations, the Nusselt number primarily depends on two variables. And those two variables are actually going to be the Reynolds number and they're going to be the Prandtl number. Okay. And so basically what we have is that Nusselt number is going to be a function of, and so that's what this F stands for, of Reynolds number and Prandtl number. Okay. And so what this tells us is that, if we have just a general fluid flow situation, if we can compute the Reynolds number and we can compute the Prandtl number, which most of the time are not that difficult to do, then what that'll do is that'll allow us to compute the Nusselt number, which will then allow us to compute H. Okay. Right. And that's basically going to be the method that we're going to be using over the next couple weeks, basically taking us up until spring break. All right. Any questions on this?
Just quickly, how is that different again from the Biot number?
Yeah, so that's a good question. So for the Biot number, this L and this K, those were for the solid, right? And so remember, when we're computing Biot number, it was the thermal conductivity of the solid itself. But for when we talk about Nusselt number, this K is actually KF. So that's going to be the thermal conductivity of the fluid itself. So all of these things are going to be fluid properties. Mm-hmm. Yeah, so mathematically it's the same, but I guess both Nusselt and both Biot, whoever those guys were, they contributed a lot to heat transfer. And so they kind of both let them both have their own number. Yeah. It's like that meme of it's like hey man, can I copy your work? Say, all right, change it a little bit. So that's I don't know which one came first. I don't know if Biot or Nusselt came first, but one of them I think clearly copied the other. They just kind of added a little modification to one. Yeah. Okay. All right. And so, from here, that was kind of just a general introduction to convection in general. And so now what we're going to do is we're going to apply this to kind of, specific situations that happen a lot in engineering. Okay. And so the first one that we're going to do, partly because, it does happen a lot in engineering, but partly also because I think it's the simplest of the bunch, is external flow convection. Okay. Okay, and so you know, when I talk about external flow, that's actually kind of the theoretical situation that I've been drawing up until this point, right? And so all external flow means is that you know you have you know, usually it's some surface that's exposed to you know a large you know, a large fluid field that's around it. Okay. And so, you know, I like to think of these situations as, you know, where, you know, the fluid basically doesn't even realize that the object is there, right? And so some situations that, you know, that might occur would be, you know, like flow over an airplane, right? And so an airplane, you know, to us, an airplane is a big object, but then compared to how vast the atmosphere is and, you know, the clouds and everything, an airplane is relatively small. And so, you know, the atmosphere and kind of all the air around it, you know, hardly knows that the airplane is there. So that's kind of a very classical kind of external flow situation. Another one could be like a boat that's you know going into the ocean and driving that way, right? And so there you have a relatively small boat compared to a very vast ocean. Okay, and so schematically, you know, we're gonna kind of simplify it as you know, flow over a flat plate. Okay, and so it looks just like this basically. Okay. And so, you know, we're going to have basically a flat plate that's going to be exposed to a fluid field. Okay. And this fluid field is going to have its free stream conditions. And so it's going to have its free stream temperature, which we call T infinity. And it's going to have its free stream velocity, which we call U infinity. Okay. And we know that, you know, as this fluid strikes the surface, a boundary layer is going to start to form on the surface. Okay. All right. And so, you know, even though we're going to be working with this, you know, relatively simple situation, you can actually apply this, you know, to a lot of engineering situations, right? And so we talk about airplanes, right? And so if you want to find, you know, heat transfer from an airplane wing out to the air, you know, that fits nicely to this, you know, to this kind of situation. Or another situation would be like on a rocket ship, right? So I think that's probably the most interesting application for this, where you have like a rocket ship, you know, leaving the atmosphere. You have basically large amounts of external air that's kind of be moving past your airplane wing pretty quickly, right? And there you also kind of have an external flow situation. All right, and so besides the flat plate, we'll also be, you know, talking about some other common situations. Okay. And so other common situations would be like flow over a cylinder. Okay. Next, we'll have a flow over a sphere. We'll have flow over a bank of cylinders. Okay. And another interesting one, which I don't think we'll get to, you know, because of time constraints. But another case is what we call an impinging jet. Right, and so for that last one, basically, that's when you like I think the most common situation, you take your hose and you spray it at a wall, right? Okay. And so let's say that we have a hose and we're spraying it and then it hits a wall, right? Okay. And so as the water hits the wall, it's going to kind of spread out, you know, on different directions on the wall. And so that's another common, you know, external convection situation. And so I think that one's really interesting, but I think, you know, it's also a bit complicated. So, you know, if we have time, you know, I do want to talk about it, but you know, I'm guessing that we're probably not going to have time. Okay. All right. Any questions on this so far? Okay. All right. And so how are we going to approach these situations, right? And so just kind of what I mentioned right before this, our goal, our ultimate goal is to solve for H. Because once you have H, then you have your convection coefficient that you can kind of do a lot of other thermal analysis with that. But the ultimate goal is going to be difficult to do, and so kind of the sub goal, or kind of the thing, our quest objective that we need to do in order to reach that goal is to compute the Nusselt number. And so Nu is our Nusselt number. Remember, it's going to be HL divided by KF, where KF is the thermal conductivity of the fluid. Right? Because once we compute Nusselt number, we can just manipulate this expression in order to solve for H. Okay? Because once we have Nusselt, we can basically say that H is equal to Nusselt number times KF divided by L. And then we're done. Okay. Right. But solving for this Nusselt number, it's a lot easier than solving for H, but it's still not a walk in the park. Okay. Because in order to compute the Nusselt number, remember the two things that we're going to have to compute along the way are going to be the Reynolds number and the Prandtl number. Okay. All right. And so, what you're going to see, over the next couple of weeks is basically a bunch of correlations in between the Nusselt number, the Reynolds number, and the Prandtl number. Okay, and these correlations were determined by a large series of experiments. Okay. And so, I do want to emphasize that, because, normally, when you have a heat transfer equation, like the heat equation that we've seen before, you can usually derive those from, fundamental principles like conservation of energy or something like that. And so these correlations here, they didn't come from something like that. So basically what happened was, some dude, or maybe some collections of dudes, basically they ran a bunch of experiments and they said, hey, this kind of, follows a general trend. Let's write an equation for it. Okay. Okay. And so let me give you kind of the first equation for this, which is your Nusselt number correlation for parallel laminar flow over a flat plate. Because what you'll see is that there's going to be different Nusselt number correlations for different situations. Okay, and so this is kind of the first situation that we have. And so if we have laminar flow and that's passing over a flat plate, what we get is the following correlation. Right? And so we have Nusselt number, and it's going to be a function of x. It's going to be equal to 0.332 times the Reynolds number x raised to the 1/2 times Prandtl number to the 1/3. Okay. And this is going to be equal to hx divided by kf. right? And so that's our first correlation, okay? And so basically to use this, you can basically, look up the Reynolds number, look up the Prandtl number, and then just plug these in here, and then, and then you can find H from here, okay? Right. And I do want to make one note here, which we'll expand upon later, is that this Nusselt number correlation, this is for a local Nusselt number and a local convection coefficient. Okay? And so, local meaning that this is just going to be the convection coefficient for just a single spot. And so in order to actually use this in calculations, what we're going to need to do is we need to average this over a surface, but we'll do that later. Okay. But, I just want to introduce the notation here so that whenever you see something with a subscript of X, what this usually means is that, this is a local quantity that, is only local to just kind of a small area. All right. Any questions on this?
Hey, Professor, you said if it has an X, that means it's local?
Yes. Yeah.
Okay. Mm-hmm. Just make sure.
Mm-hmm. Okay. All right. And so how do we go about actually computing this? So as you can see, from that expression, we're going to have to plug in a lot of fluid properties into this expression. Okay. Right. So, from the previous expression, you can see at the very least, we have the thermal conductivity of the fluid, so Kf, right? And we also have Reynolds number, so that's going to depend on the viscosity, okay? And then we have Prandtl number, which is going to depend on viscosity and thermal conductivity, or thermal diffusivity, okay? And so there's a lot of properties that we're working with, right? The complicated thing here is that, a lot of these fluid properties actually their values actually depend on the temperature of the fluid. Okay. And so, as an example, let me list out some of the viscosity values for water at various temperatures. Okay. And so on the left, I'm going to have the temperature, and this is going to be in degrees Celsius. And on the right, and list out the viscosity. And these are going to be meters squared per second. Okay. All right. And so if you have, water that's basically freezing, and so we have water at 0 degrees C, the viscosity is going to be 1.787. Okay. And we raise the temperature up and the viscosity by 5 degrees, and our viscosity is going to drop to 1.519. Okay. We increase again to 10 degrees. Okay. And the viscosity becomes 1.307. Okay. Then we go up to 20, and then the viscosity drops to 1.004. Okay, 30, and then this viscosity drops again to 0.801, 40, and then our viscosity drops to 0.658. And let's do one more, 50. If our fluid is 50 degrees, if our water is 50 degrees C, then our viscosity goes, down to 0.553. Okay. Okay. And so you can see here, there's a huge difference. And so if you compare the viscosity, when the water is almost freezing compared to when it's hot, we have a huge range of viscosities here. So it almost goes, from 50 degrees C up to 0. that's almost like over a 3 times difference in between them. Okay. Okay. And so, so why do I mention this, right? And so, like, who cares if the property, properties change with temperature? Because this kind of gives us a problem. Because, oftentimes what's going to happen in these situations is that, we're going to have very different temperatures, or we're going to have our temperature's going to, vary pretty significantly in the thermal boundary layer. Okay. And so just as an example, let's say that we have water that's flowing past, a flat plate. What if our plate, our surface here was at a temperature of 50 degrees Celsius, but then our water, the water that we're flowing over it is much colder. Right? So what if we have a free stream temperature of 10 degrees Celsius? Okay. Right. And so, when we have these differences in temperatures, we'll, at this point, we're going to go in and say, okay, I want to compute the Reynolds number here. In order to do that, I need to plug in the viscosity. Okay. But, do I plug in, 1.03 because that's the fluid, that's the temperature of the free stream? Or do I plug in, 50, because that's the temperature of the surface. And so, the fluid that's really close to there, right? And so you can see there's a big difference, and whether you plug in 0.553 or 1.307, it's going to have a big impact on your results. Okay? And so, there's kind of this question right now of, what temperature do we evaluate our fluid properties at? Okay. All right. Any questions on this so far? Okay. All right. And so let me kind of just draw an image of, of kind of the problem that we have, right? And so let's say that we have a surface, okay? And we can say that the temperature of the surface, we'll say, is 50 degrees C. Meanwhile, we have a fluid that's blowing over the top. And then the fluid temperature itself is going to be 10 degrees C. Okay. Okay. And so for these situations, actually, probably, the most intuitive situation, the most intuitive solution actually comes to, becomes a thing. And so what we can compute from here is we can compute something called a film temperature. And the film temperature is just going to be basically just the average in between these two extremes. And so TF in this case is basically just going to be TS plus T infinity, and then we're just going to divide it by 2. Okay. All right. And so it's literally just the average. Okay. And then once we compute this film temperature, we can use this temperature to evaluate our fluid properties. Okay. Right. And so in the example that I've shown here, what we can do is we can compute TF. And TF is going to be the average between TS, which is 50, plus 10, which is T infinity, divided by 2. And so the average of that is simply just going to be 30 degrees C. And then now that we have 30 degrees C, we can use this to compute the viscosity. Right. And so at 30 degrees C, we can see that we have a viscosity of 0.801. Okay, and so we can say that nu is equal to 0.801 meter square per second. Okay, and now we can plug this into our Reynolds number, and then we can use that to compute Nusselt number. Okay. All right. Any questions on this so far? Okay. All right. And so now let's talk about how we can actually use the Nusselt number. And so in fact, let's talk about the difference between the local Nusselt number and the average one. Okay. Because remember, there's a difference kind of between the average convection coefficient and the local one. Okay. And so in particular, we have this equation that we saw last time. Okay. So this H bar here is the average convection coefficient. And the way that we computed that was we did 1 over L. We integrated from 0 to L of the local convection coefficient as a function of x. Okay. Right. And so what we can do is we can use this to compute use this expression here to compute an average Nusselt number correlation. Because the Nusselt number correlation that we have right now is actually not that useful because it's a local quantity, right? And so right now we have NUX, and this is equal to HX times L divided by KF. So I'm sorry, HX X, okay? Okay. And this is equal to 0.332 Reynolds number x to the 1/2 times Prandtl number to the 1/3. Okay. All right. And so I'm going to take this expression right here, the one that I have in square brackets, and then I'm going to use it to solve for hx. Okay. And so I'm going to divide both sides by x, and then we're going to work with that. Okay. In particular, I'm going to take this Reynolds number and I'm going to expand this out. So this Reynolds number is going to be nothing more than U infinity times x divided by nu. Okay. All right. And so if we solve for hx, okay. And so we're going to multiply both sides by kf, and so that's going to get rid of kf on the denominator, and then we're going to divide both sides by x. And so what that gives us is the following. And so what we get is hx of x is equal to 0.332 times kf times u infinity divided by nu raised to the 1/2. Okay. Then we have x raised to the minus 1/2, and then Prandtl number to the 1/3. Okay. And so this x to the minus 1/2, this shows up here because we divided both sides by x. Okay. And we already had an x to the 1/2 that was present from the Reynolds number. Okay. And so when you divide by x, that becomes x to the minus 1/2. Okay. And so what we can do from here is we can take this and plug it into our expression for up here. And so we're going to be integrating it And then that will help us compute an expression for the average Nusselt number. Okay. All right, any questions on this? Okay. All right, and so let's go ahead and plug it in. And so we're going to have basically h bar is equal to 1 over L integral from 0 to L of hx of x dx. Right? And so if we plug in for that, what we get is 1 over L integral from 0 to L of 0.332 times kf times u infinity divided by nu to the 1/2 times x to the minus 1/2 times Prandtl to the 1/3 dx. Okay. Most of these quantities are constants, and so I'm just going to pull all of them out. And so the only one that's not a constant is just going to be this x to the minus 1/2, which is what we're going to be integrating over. Okay. Right. And so if we kind of simplify this a bit, what we get is 1 over L times 0.332 times kf times u infinity divided by nu raised to the 1/2, okay, times Prandtl number to the 1/3. Prandtl number is just a constant here as well. And then we have integral from 0 to L, x to the minus 1/2 dx. Okay. All right. And so from here, we can go ahead and perform this integral. If we perform that integral, what we get is 1 over L, 0.332 kf times u infinity divided by nu to the 1/2, Prandtl to the 1/3. And so if we perform this integral, what we get is 2x to the 1/2 evaluated from 0 to L, right? Okay. And so what we get from this, and when we evaluate it from 0 to L, all we get is 2 times L to the 1/2. Okay. All right. And so if we kind of work this through, then what we get is equal to 1 over L 0.332 kf u infinity divided by nu raised to the 1/2 times Prandtl number to the 1/3. Okay. Actually, let me multiply that 2 throughout, and so that 2 is going to turn this into 0.664. Okay. And then we still have L to the 1/2 here. Okay. And this is equal to h bar. Okay. Right. And so we're almost done, because what we're going to do to this expression is we're going to multiply it by L, and we're going to divide by kf. Okay. And we're going to do that to both sides of this equation. And so, you know, on one side of the equation, on the left-hand side, we can see that L is going to cancel out with this, and the kf is going to cancel out with that. Okay. And so we're going to have 0.664 times. I'm going to take this L to the 1/2 and bring it into this 1/2 here. And so we have u infinity L divided by nu, all raised to the 1/2 times Prandtl number to the 1/3. And this is equal to h bar times L divided by kf. Okay. Okay. And you can see now that we've obtained HL over K again, and so this is the same as our Nusselt number. Okay. But now this Nusselt number has a bar over the top because this is the average Nusselt number. Okay. And then what we see from this expression right here, this expression in the 1/2, this is nothing more than just our Reynolds number. Okay, so let me go ahead and replace this. And so this is basically just going to be our Reynolds number raised to the 1/2 power. Okay. And so what we have here is an expression for the average Nusselt number over a flat plate. Okay. Okay. And remember, this is for laminar flow, and so you basically have to make sure that the flow here is laminar. Okay. All right. Any questions on this before we do an example? Okay. And so I think probably I'll start this example now, and then we'll probably finish this up on Monday because we are running a little bit short on time. So for now, we're going to do laminar flow, but then, what we'll see next week is, how these correlations change for turbulent flow. And so whether your flow is laminar or turbulent, that's going to be kind of a branching point in your solution kind of, hierarchy. Because basically what's going to happen for turbulent flows, you're going to use a different correlation. Okay. All right. And so let's say that we have laminar flow of air over a flat plate. Okay. And let's say that the air has a pressure of 60 kilopascals, or 6 kilopascals, sorry. Okay. And so that's going to come into effect later. Okay. And I guess this air is really hot. We must be on like Saturn or something, or the sun. Okay. Because the temperature of this air is going to be 300 degrees C. Okay. And it flows over a plate that's half a meter long, and has a velocity of 10 meters per second. Okay. And also the surface temperature of this plate is 27 degrees C. Okay, and so let's draw kind of a schematic of this situation. Right, and so we're going to have our flat plate. We're going to have our flow. And so we have our dimensions for the flow. And so we have T infinity. T infinity here is going to be 300 degrees C. Okay. U infinity is going to be 10 meters per second. And P infinity, which is the pressure of this flow, is going to be 60 kPa. Okay. We also know the surface temperature. So surface temperature is going to be 27 degrees C. And then the length of the plate is going to be half a meter. So it's going to be 0.5 meters. Okay. All right. And so what we want to solve for is we want to solve for the amount of heat transfer or the amount of heat that gets transferred from the fluid to the plate.
Professor, is P infinity 6 or 60?
Oh, it's 6. Sorry. I'm thinking of something else, but it's 6. Yeah. Thank you. Okay. All right. And so here, we have a pretty classical, convection, heat transfer situation. And so to compute this heat transfer from the from the fluid to the plate, what we can use here is just our classic Newton's law of cooling. Okay. And so this is, the same as we always have. And so we're going to have Q is equal to H bar A times T infinity minus TS. Okay. Great. And so same as we always have. Okay. Okay. The only difference here is that, nowhere in this problem were we given H. Okay. And so in order to solve for the heat transfer from the fluid to the plate, we're going to need to solve for H here. Okay. Oh, and let's assume that into the page, this plate has a width. This plate has a width of 1 meter, and so we can kind of just ignore that. Okay. All right. So any questions on the problem setup? Okay. All right. And so in order to complete this calculation, we need to compute H, and in particular, since we want to use Newton's law of cooling, the H that we're going to compute here is the average H. Because you're seldom going to use the local H quantity, because remember the local H changes at every location on your plate, and so if you're going to compute something like an overall heat transfer, most of the time you're going to work with an average one. Okay. All right, and so to compute this, we're going to use our Nusselt number correlation for the average one. Okay. And so that Nusselt number correlation is given by the following. And so NUX with the bar over it, or I guess it's just NU with the bar. Okay. And so NU bar is going to be H bar times L divided by KF, which is equal to 0.664 Reynolds number to the 1/2 and Prandtl number to the 1/3. Okay. All right. And so in order to proceed, what we're going to need to do is we need to compute Reynolds number, and we need to compute Prandtl number. Okay. All right, so the first thing that we need to do is, in order to compute the Reynolds number and the Prandtl number, is we need to look up the properties of air at the appropriate temperature. And the appropriate temperature that we're going to look up things up with is going to be the film temperature. Okay. Right. Because remember, we have a huge difference here, and so our air here over the top is at 300 degrees C, which is insanely hot, and then we have our surface here, which is at 27 degrees C, which is less than 10 times, more than 90% lower than that. That was a big thunderclap. Okay. And so in order to compute in order to evaluate the properties, we need to do this at the film temperature, which is going to be right in the middle of these guys. Okay. And so the film temperature, we're going to take T infinity plus TS divided by 2. And what we get from this is 163.5 degrees C. And then I'm going to convert this to Kelvin, because a lot of these tables are, they have you look things up in Kelvin. So this can be 436.5 Kelvin. Okay. All right. And so there's our film temperature. And so now that we know our film temperature, we can look up these properties And you can either, you can either look these up online, and so you can, there's a bunch of data tables online. But if you have the textbook, you can look these up in table A.4. Okay, and so it's in one of the appendices of the book. Okay, and what you'll see from this table is that this gives you the properties of air at 473 degrees K, which is pretty close to what we have, and 1 ATM. Okay. And then we have the following. Okay. And so the viscosity is going to be 30.84 times 10 to the minus 6 meters squared per second. KF. This is going to be 36.4 times 10 to the minus 3 watts per meter K. And then the Prandtl number, which you can look up straight from the table, is going to be 0.687. And so a big part of this chapter is going to be, just looking up properties in a table, and then using those for your calculations. So, be prepared to look a lot of things up. Okay. All right. Any questions on this? Okay. All right, and so one thing to note here, and I'll say that this is not very common, at least for the problems that I'm going to give you. But what you'll notice is that these properties are given to you at 1 ATM, right? So 1 ATM is about about 100 kilopascals. Okay? And so our gas here, or our air, is at a much lower pressure than this, and so our air is actually at a pressure of 6 kilopascals. Okay? And so that's going to change our property values as well. But luckily for us, things like the thermal conductivity and the Prandtl number, these things usually don't change with pressure. Okay. But the viscosity does. And so we're going to need to modify our viscosity value, according to the pressure. Okay. All right. But luckily, the way that we do this is actually, pretty simple. Okay. And so the way that we do this is we basically just take the ratio between 1 ATM and our current pressure. Okay. Right. And then of course, we need to convert 1 ATM to kilopascals. 1 ATM is basically 101.33 kPa. Okay. And then we're going to multiply this by the viscosity that we get. Okay, so that's this right here, this 30.84 times 10 to the minus 6 meters squared seconds. That's the viscosity that we looked up. And so to basically adjust this viscosity according to its current pressure, what we get is 5.21 times 10 to the minus 4 meters squared per second. Okay. And so you can see it makes a big difference. And so the pressure values change how we modify these things. Okay. And so now that we have all the properties, we're ready to kind of plug everything in. Okay. Okay. And so first thing we're going to compute here is the Reynolds number. And so the Reynolds number is just going to be U infinity times L divided by nu. Okay. And so we have all these properties given to us either from the problem, or we just looked it up. And then what we get from that is 9597. Okay. Okay. And now that we have the Reynolds number, we can go ahead and compute the average Nusselt number. Okay. And so the average Nusselt number is going to be, we're just going to plug it into our correlation. And so it's 0.664 times our Reynolds number raised to the 1/2 times our Prandtl number. And so our Prandtl number was 0.687 raised that to the 1/3. Okay. And this is going to be 57.4. Okay. Okay. And then from here we can compute h bar, because h bar is simply just going to be our Nusselt number times kf over L. Okay. And then we get an h value of 4.18 watts per meter squared K. Okay. Right. And so basically, you know, once you compute all the properties and all that stuff, there's just kind of a lot of plugging in, and you know, there's kind of a big cascade for all this stuff. Right? So I know I'm out of time right now, but you know, there's just one more step, and so all we have to do after this is just plug this into our Newton's law of cooling equation. Okay. Because we have h, you know, we have, you know, the area we can compute from the dimensions of the problem, and we also have the temperature difference. So everything that we need to solve for Q. All right. So any questions on this before I kind of do just the last step of this example? Okay. All right. And so the last step is just basically just plug it in and solve for Q. And so we have Q is equal to H, which is 4.18 watts per meter squared, okay, times A. A here is just going to be 0.5 meters times 1 meter, which was the width into the page, times the temperature difference, which is 300 degrees C minus 27 degrees C. And then what we get from that is 570 watts per watts. Okay. All right. And so this example basically just kind of gave you a little bit of an appetizer of the kinds of problems that we're going to be doing. Okay. And so, you know, basically what we're going to be doing is, you know, we're going to take our Nusselt number correlations, compute all the properties for it, and then use that to solve for H, and then go from there. Okay. All right. Any final questions on this before we wrap up for the week? Okay. All right, so thank you guys for tuning in this week. So I apologize for running over a couple minutes. And so, you know, have a great weekend, everyone. I haven't assigned homework for yet, and so I'll do that on Monday. But you know, I wanted to give you guys a week break after the exam. So you know, there's nothing to assign yet, but you know, look forward to one on Monday. So have a great weekend, everyone. You know, stay safe. So I know it's raining a lot out there, and I'll see you on Monday.
Thank you, Professor. Have a good weekend.
Thanks, you too. Thanks, guys.
Thank you, Professor.
Thanks, guys.